All right. Hello, everybody, and a warm welcome to part 2 of our new webinar series, In-Depth Application Knowledge from Experts. It is a pleasure for me to guide you through today's webinar, and I'm very happy to see so many of you joining today from all over the world. So this is also a good evening to our Asian friends, a hello to our European listeners, and a good morning to our US audience. Many of you already know SCAN. SCAN is a leading provider of online water quality monitoring systems. With more than 20 years of experience, and since the year 2020, we are also a proud part of Meter. We have prepared an exciting webinar series for you where our SCAN experts talk about different water quality monitoring applications. The recording for part 1, which was about wastewater, is already available on our website. And today, or in December, you will get a chance to hear about environmental monitoring. And today we will focus about drinking water production and distribution. Shown applications will range from well monitoring to a plant survey and also distribution network monitoring. Today's presenter is Christoph Wagner. He's a chemical engineer by training that focuses on process analytics using spectroscopy during his work as a research assistant, and since a few years he's now in charge of product and innovation management at SCAN. At the end of this session, you will have the chance to ask questions, and they will be answered. Before we begin, we also have a few webinar guidelines for you. Your microphone will be muted to reduce background noise and allow the best sound experience for all our participants. Use the questions function to collect your questions to avoid confused talking. You can find them in your panel on the right side. These questions will be answered at the end during the question and answer session. And if we run out of time, all questions will be collected and made available for you to read on our customer portal. As I mentioned, the video of the full recording will be available on our website after the webinar. With this, I will hand over to Christoph.
Thank you. The slides are gone now.
They're coming back. Here you go.
Okay, so thank you for the introduction and welcome to everyone to this second part of this webinar series. And it's my pleasure to walk you through applications in drinking water here at SCAN. Now let's see if the slides move. Okay, so for those of you that have joined the past session, this is a familiar picture of you. This is like showing the circle of water with the clean water applications, the environmental monitoring applications in dark blue, the wastewater applications that my colleague Franz covered in the last webinar, and in between the industrial applications which are not part of this webinar series. For today, we are going to focus on that part. So I want to cover examples from raw water monitoring that is used for drinking water production itself, and then go into the distribution network. The applications that I want to cover is not much about surface water monitoring, because this will be part of the environmental monitoring part. But bank filtration is a topic, groundwater monitoring is a topic, the operation control of the drinking water plant, and then obviously number 5, distribution network monitoring. The typical applications that we cover for surface water monitoring are intake protection that is combined with a contamination alarm that we can do with our systems to make sure that no contaminants get or reach the drinking water distribution plant that are difficult to treat there, for example. Another application of surface water monitoring would be if you have different raw water sources available, for example, a river and a groundwater source, and you blend these two water sources in your process to produce drinking water. And one very important part, and this will also be part of the treatment plants, is feed-forward control. So where you use data that you generate from in the raw water to feed this information to the plant, and the plant knows in advance what's going to come into the plant and can adjust the treatment process accordingly. Then this is very laggy here. I can't move the slides anymore. Vicky, can you move to the next slide, please? Okay, so bank filtration monitoring, part of the, whoops, oh, we are much too fast. Very interesting. Okay, bank filtration monitoring. Managed aquifer recharge is one topic where you use water to top off the groundwater level, but very important is monitoring of filter efficiencies if you're talking about bank filtration. So where you have the monitoring wells close to the actual river bank, and the river pushes water into the groundwater, and this is then taken for drinking water production. Of course, their turbidity monitoring is important. For example, if you have small flooding events, we will see an example of that later on. And obviously also contamination alarms. So if you have an accident with a ship, for example, on the river, and this gets into the water and then is pushed into the bank filtrate, this is also not optimal to get into a treatment plant, of course. So groundwater monitoring, I mean, the main application in this application is obviously nitrate monitoring. We have a limit of 50 milligrams per liter of nitrates in drinking water in Europe and in most other countries, or even less. And nitrate is one of the most used fertilizers, together with ammonia and phosphate, obviously. And if you have over-fertilization, the nitrate can find its way into the groundwater. And the nasty thing about nitrate is that it's very hard to remove by treatment process. It's very expensive. So the lower the concentrations in the groundwater, the better, and it's really hard to remove. Other parameters that are commonly monitored in groundwater is dissolved oxygen, conductivity, and turbidity and organics, like the total organics or the dissolved organic carbon. And the operation of the plant where our sensors are used is, for one part, is this coagulation control. We already talked about this. It's about turbidity in the first place, but then also organics and color that need to be removed, because we all expect clear and colorless drinking water, and everything that disturbs this has to be removed during the cleanup process in the drinking water work. Then some of the drinking water works use ozonation in their treatment process, and we can monitor this ozone in the water to control this process. We have applications where we monitor the filtration steps in the drinking water, for example, for turbidity removal, organics removal. Of course, the final quality control becomes more and more a topic since this year in January, the new European Drinking Water Directive is into effect. And for the first time ever, there is a mandatory online monitoring necessary in the European Union, as in particular drinking water works that supply greater than 10,000 households and use a filtration system in their cleanup process need to have a mandatory turbidity monitor at the outlet into the drinking water works. The reason is that if you have a major filter breakthrough, you get turbidity, but also, for example, maybe bacterial cells flushed into the drinking water network, which then cause negative effects on the network. So for the first time ever, this is becoming mandatory now. And last but not least, for drinking water systems that use disinfectants in the drinking water network, we can monitor the disinfections like free chlorine, the chloramines, total chlorine, chlorine dioxide, and also dose the chemicals into the drinking water system together with our partner Grundfos that has these stations readily available. And last but not least, the drinking water network monitoring. In the drinking water network, of course, you want to know immediately if something is happening to the quality of your water. So this would be the contamination alarm. It's the closest to the customers, and also with the new drinking water directive, you have this source to tap approach where you have a risk-based approach to the quality of the drinking water, and this monitoring in the network can be a very valuable part in these risk-based documents that you have to provide now. You can monitor the hygienical risk. If you have organic carbon available, this is nutrients for bacterial cells that can feed on this. In combination with the temperature, the higher the temperature get, the faster these bacterial cells can grow. And if this comes together with a lack of disinfectant, for example, then it's very likely that you get some bacterial growth in your drinking water network that can then have negative effects on the quality. We can monitor the flushing of the network. So when providers emptied pipes for maintenance issues, then they need to flush this with chlorinated water, high chlorine concentrations, and we can monitor this flushing. We can see turbidity, organics, and of course we can also monitor the water quality in reverse flows situation. For example, when they use district metered areas, DMAs, and they reverse the flow in one of these DMAs for leak detection and so on. And then we can also monitor the quality of the water. And before we now jump into the applications directly, or the case studies, I want to spend a little bit of time on spectroscopy, not only because I'm a spectroscopist by education, but because it's key to what we do here at SCAN. So what we do is we use light to measure substances in water. And what we do is we shine light through the water sample, and the intensity at the beginning, before the water reaches, that the light reaches the water, is I0, so the original intensity, and during the light passes through the water sample, light gets absorbed. And what we see at the end is reduced by the amount of energy that was absorbed by molecules dissolved in water. And if you take this I divided by I0 and take the negative decadic logarithm, you end up with the absorption. And this is what we usually deal with here at SCAN. And the beauty about absorption is that it's linearly scaling with the concentration of a molecule, a natural constant epsilon that tells us how strongly each of the molecules absorbs lights. And then the last factor is the open path length, or the interaction length that the light has with the water sample. So the OPL is fixed by the spectrometer. So we have a linear scaling from the absorption to the concentration. And this can look, for example, like that. The substance A exhibits this blue absorption curve. And if we mix substance A with a second substance B in the same water sample, we end up with the sum of both signals. So very, very easy to understand, but I'm pretty sure that most of you already think that it can't be that simple, and that's true. If we look into a typical water sample, we get more or less something looking like that. The spectrometer in a typical water sample sees this blue curve, and this blue curve is what we call the non-compensated spectrum. This non-compensated spectrum contains information on dissolved and non-dissolved substances, so particles as well. Particles have a second interaction with light, they diffract light. So it's not it's absorbing the light, but the light is lost by diffraction. And this diffraction causes this upward shift and this tilt of the baseline that we see here in blue. And what we can do then mathematically is subtract the influence of this particle diffraction. And what we end up then with is the red curve that you see down there. And this is the absorption spectrum we usually work with. And this is kind of separated in 3 parts. The visible part, where you see mainly the turbidity influence, this diffraction. You see color. For example, here we see some absorption in the blue spectral region. This means that this water sample would look yellowish to the eye because the blue color is absorbed by the molecules and missing for us to see. Then we have the second part there, which is about the organic molecules that are dissolved in the water. Here in this region, we can measure chemical oxygen demand, biological oxygen demand, total organic carbon, the dissolved organic carbon. And if we go further into the UV, we reach an area where we can measure the nitrites and nitrates for example, fish farming application. And what's very nice about monitoring spectral data online over time is that you can record them, for example, every 2 minutes, every 5 minutes. And if you look at the 3D representation of the spectra, you see immediately 2 events that happened in this graph. The first one here, at 7 o'clock in the morning, there was obviously something added absorbing in the blue, so making the water look yellowish. And on the next day in the morning at 7 o'clock, you can see the same event happening. But at the same time, if you look at this UV part that is not that prominent, you can also see that there is like at midnight, around midnight, you see the organics go up and so on. And how do we measure this? We use our spectrometer probe to do so. This has an xenon flash lamp sitting here at the front that emits the light over a broad spectral range, so from the visible to the UV. This light passes through 2 beam paths, through the measuring beam, but also through the internal beam, and then the light is diffracted by grating on 256 pixels of a detector, and this gives us this wavelength information that we need to calculate this absorption spectrum. Before we run the measurement itself, we use this internal path to record this background spectrum that I mentioned before, this I0. And as soon as we have done this, we run it through the measurement beam, and then we get the I value that we need to calculate the absorption. You see here, this here is this open path length that we can influence. 35 millimeters, as you see here, is typically used for drinking water applications. Environmental monitoring would use 5 millimeters, and wastewater applications usually 1 millimeter of absorption path length, because the higher the concentrations, the smaller we want to make the open path length to keep the absorption value approximately in the same range, which is important for the calculations. And what do we do with the information that we generate with our sensors, not just with the spectralizer, but also with the other sensors like the chlorine, conductivity, pH? We can feed them into our data validation and the event detection software. What you see here in blue, this blue, the data from the probes, as we would call it raw data, comes in here, is passed into the data validation software called ValiTool. There we look for abnormal patterns like increased noise levels, unexpected jumps in data points, and so on, to make sure that the data that we pass on to the event detection software after validation is clean from any outliers, because we of course don't want to detect outliers in this drinking water protection scenarios. And then we have this ANA toolbox that we use for event detection, and this can flag data points as events, and this information is immediately fed back to the operators in charge that then evaluate this data and can also train these algorithms. This was a valid event, this was a false alarm, and so the system learns, and the cycle is kind of closed. And now I want to talk a little bit more about this event detection because it's an integral part for the drinking water applications. And why do we use event detection software in the first place? It's very simple. It's much more powerful than using simple thresholds. For chlorination, for example, it's not that difficult. You have a limit of chlorine you want to have in your network, and you set this threshold, and if the level drops below this threshold, you can say, okay, something's wrong. But sometimes it's not that simple, and the combination of different parameters is the powerful thing. And it's correlates different inputs, and it kind of is with this picture here, it all fits together, and then in this puzzle, and then you have this event, which not necessarily means just one parameter drop below a certain limit. And to illustrate this a little bit further, what our system does, it combines multiple parameters. In this case, it's parameter 1 and parameter 2, and all these blue dots that you see there are basically what is regarded normal by the system. And of course, you can add a third parameter, then it's getting 3-dimensional, a fourth one, 4-dimensional, and so on. And when you run a new measurement, and it's the data point that is measured in this parameter space ends up with the green dot, we have this distances defined from this green dot to the blue ones. And if this is close enough to the blue dots, the alarm value is not exceeded. So the system regards this measurement as a normal measurement. But if the same measurement would lie at this red dot, it's too far away from the blue normal measurements, and an alarm value would be raised. And we can take it even further when we look at the spectral information that we get from the spectralizer. And in this case, what we have, or I want to show you some theoretical examples first. We have this UV254 absorption here on the y-axis, and different contaminants on the x-axis, so like the benzene and the PTX substances and the de-icer substance from an aeroplane or from an airport. And then under laboratory conditions, it's very easy to single out these absorptions, and the ability to detect each of these contaminants is kind of only limited by the precision of your detection principle, so like the GCMS or whatever. But if you want to do this online in real time, things look a bit different, and this is because of all the other influences that come from the water source. So we don't have only the contaminations, but we have particles, the cause turbidity, we have a natural organic background, and in reality the line more looks like the green one that we see here. And if you like rotate this spectrum, you see kind of the green UV254 values that we have seen in the past slide. They are all within the normal fluctuation range of your water matrix. And if you measure a data point like this blue one here, this is well within all the natural fluctuations. So you can't say, is this caused by a contamination, or is this simply the natural background? And just adding a second wavelength to this picture clears everything a little bit up. You see that the contaminants start to separate from the natural fluctuations. And now everyone would say, okay, the blue dot is well within the green natural fluctuation, and we look at a normal measurement here. And we can, of course, add more and more wavelength to this to clear up this picture. So one wavelength, the alarm value very low, 0.4. If we add a second one, we see the contaminants come out much clearer already. If we add use 5 wavelengths, we start toluene, for example, to come out of the noise, but the alarm value is still very low. And if we add a complete spectrum, like from the spectralizer, then we can separate out all these contaminants very clearly now. And with that, enough from the theoretical background. I just wanted to cover the spectral data because we will see some information, and we will also see some alarms that we've seen. And I just wanted to make you comfortable with the background of what you will see. And now let's jump into the case studies. So as mentioned, I will not show any case studies from surface water because this will be covered in the environmental section. But I will show you something about groundwater and bank filtrate in a second. And I want to start with our home supplier here in Vienna, the Vienna Waterworks. Some background information. Vienna is very blessed with a lot of springs that are actually located quite far away from Vienna in Lower Austria and in Styria. And we have two spring water pipelines that transport this water to Vienna just by gravity. So it's running down the gravity from the mountains. For the first Vienna water pipeline, which is 150 kilometers long, it takes the water about 24 hours to travel all the way towards Vienna. We have the second pipeline, 180 kilometers long, 36 hours. It takes the water to reach Vienna. But in summer times when demand is really high, we also have some bank filtrate that comes from the Danube Island or from the Lobau Natural Reserve. And last but not least, if it's really necessary, we have a well field located south of Vienna that can even also supply 64 million liters of water per day. 3,000 kilometers of pipes, 29 gravity reservoirs just within Vienna that are filled with this water and then are used to distribute the water to the households, which are around 103,000 house connections at the moment. And all these pipelines, all these wells, all this bank filtrate is monitored with S-scan sensors to give you some impressions how this looks. This is the most prestigious spring we have. It's called the Kaiserquelle, which is called after the former Austrian emperor. You can't see our sensors, but they are located all the way down on this rod here down in the water. Not all of them look that pretty. If you look at the bank filtrate monitoring station at the Danube, it looks more like a lab. The spectrometer sits down here in the flow cell, and we have a conductivity sensor sitting here, feeding in one of the terminals. Another example from one of the springs in Styria. This is actually a submerged installation that was taken out for maintenance. You see the spectrometer here. Usually it would go all the way down into the water on this rail here. And last but not least, all the reservoirs in Vienna also are equipped with a spectrometer and at least a conductivity sensor. And now some data. In total, it's over 70 stations, and everything is monitored with one or the other type of S-scan sensors. All of them are equipped with a spectrolyzer. And one example, what can happen if you have a heavy rainfall event in one of the catchment areas of one of these springs. Very quickly after the rainfall, turbidity goes up in the spring water. At the same time, if you would look only at conductivity, you would not see any change or very little change here. And as soon as the rainfall stops, over a few days, turbidity goes back to a normal level. But if you look at the blue curve, which is the spectral absorption coefficient, so it's a measure for the organic matter that is dissolved in the water, you see that there is a lag, in this case, for the organics to go up, and it has a quite delay to bring down the organics. And what we do, because we have so much water in Vienna, is we simply monitor the quality, and if it's not good enough, we just discard the water. So if you would discard the water just by looking at turbidity, you would feed a lot of organic matter into the raw water pipelines. This is avoided by monitoring the water, not just with the classical sensor systems, but also with a spectrometer. Another example from one of the springs in Styria, you can see there. Actually, you can see 3 events here. The first one, maybe not that prominent, was only picked up by conductivity, so it's not seen in turbidity or organics. The second one was only picked up by the turbidity sensor. And the third one and most prominent one was obviously causing a major disturbance in conductivity, but also in dissolved organic carbon. Only very short peaks in turbidity, and then turbidity would be back at normal levels, but not the organics. So this is kind of to illustrate that it's really, really important to combine different sensors with thresholds, with pattern alarms, to be sure to catch all events that can be seen here. Another example from the second Vienna spring pipeline, I said, okay, we monitor the pipeline all the way towards Vienna, and there's a final control in Vienna. And what you see here is a turbidity event that made its way into the pipeline. And around 1 o'clock in the morning, it was seen by this station, and then the water traveled along the pipeline by gravity towards Vienna. 8 kilometers later, it was around 4 o'clock in the morning, and we could follow this event all the way towards Vienna. And again, what we did is we just discarded the water before it actually reached the Viennese reservoirs. So it's a very nice example that how you can monitor from the springs, in our case, over the whole transportation pipeline into the reservoirs. And now enough from springs, and let's jump into a bank filtrate example from the Danube River in this case. We have 4 different bank filtration wells that feed into the same gathering station, and the main line that gets into the works is monitored with one of our pipe scans. And what you see there is conductivity on the top, temperature, pH, redox potential, UV 254, turbidity in this case. And the last graph at the bottom is actually the water level of the Danube. And what you see there on August 3rd, there was actually a flooding event. So it went from 300 centimeters all the way up to 600 centimeters. And then the water level went down back to normal. And what's interesting to see is that there's actually a lag from this flooding event to the change in water quality. So if you look here, the flooding event was already over, and now the UV 254 value, which is again a measure for the organic content, starts to rise, and then with a delay of a couple of days, it starts to relax. So a little very similar to what we've seen from the springs. And what is also very obvious to see here is the switching between the different wells. All of them exhibit different characteristics, and whenever they switch from one well to another one for the pumping, you see the differences in the water quality. So next example, groundwater monitoring. We have a very intensive nitrate monitoring in Vienna, in Austria. You see the map of Austria here, and each of these green dots is one groundwater monitoring station. And ESCAN has a lot of sensors located down there in the southern part of Styria, very close to the border to Slovenia. And for many years, we monitor the nitrate levels there that are quite high for Austrian means. And I want to show you some example. The sensors that are used there look like on this right picture. At the very bottom, you have a conductivity sensor, a condolyzer. In the middle, a dissolved oxygen sensor. And on top here, that's the spectrometer sensor with the cleaning brush sitting here. And our research partner that runs these measurement locations did a very intensive monitoring or comparison between what our sensor reads and what the lab method actually gets, and this is what you see there. And up there in this graph you see the nitrate level for one of these wells that was around 32 milligrams per liter, and then at the end of November it started to rise to like 33.5, and then it went back down again. If you zoom out a little bit and not just look at a few months but a few years of data that you measured there, now we have like 3 years of data. The gray curve is what the spectralizer was reading. The black crosses are the reference values that were analyzed in the lab, and in red you see the residual nitrate concentration. This was all the measurements that we did were within plus minus 1.2 milligrams per liter, which was pretty amazing for them to see in the range of 35 to 38. And just a reminder, it's 50 milligrams per liter, that is the threshold in Europe. And what the drinking water providers in this region do is they monitor the groundwater in special wells upstream of the actual production wells that they use for drinking water production. And they have models in the background that allow them to know where they need to pump out the groundwater so that the groundwater flows start mixing in a certain way so that the nitrate concentrations they get into the production facilities are always below the threshold of 50 milligrams per liter. So with that, we change to the second step in the drinking water production, the operational control in the drinking water plant. And I picked one story from a plant in Denmark. And you see the operational schematic up there. Raw water comes into the plant, is split up into two streams. Coagulants and flocculants are added in the flocculation system. The turbidity is removed. Then they have a pH control by adding sodium hydroxide. Then each of these streams is split up again into two. There's an ozonation treatment step. Then there's something very interesting. There's a biological filter. So bacterial cells consume the organic matter in the water. After that, there's a granulated activated charcoal filter. Then the whole water gets disinfected by UV lights, so to make 100% sure that no bacterial cells get into the drinking water network. Then there is a chlorination step, a buffer tank, and after that the streams are combined and a final quality control step is done before it goes into the network. And we did a survey on this plant, and every red dot here was a location where we took spectra to evaluate the performance of this plant. And I want to show you some data right now. This is the overall view, the inlet in black. You see, if you remember, there was this tilt and this upward shift in the spectrum caused by turbidity, followed by the organic matter in this part, and some the nitrate and nitrite here at the very end. And after the initial flocculation, we end up with the blue spectrum. So a lot of turbidity, a lot of organics are removed from the water already. Then as next step, you have the ozonation. Now the spectrum shifts upward, which is counterintuitive, but it's very normal that this happens. The reason is that using ozone breaks down large organic molecules into smaller molecules. So like humic acids, for example, they are broken down into smaller parts, and these smaller molecules have more UV active groups, and this is why we see an increase in the spectrum. Then next step is this biological filter called anthracite filter here. You see that after this filter, most of the organic is gone, and after the granulated active charcoal filter, there's nothing happening anymore to the organics. And just to put this into perspective, the drinking water that we get in Vienna from the springs has the quality of the water after this biological filtration step. But the operators of the plant, they wanted to know even more about how their process works and how well it works, and this is why we did some more extensive field work with them. What you see there is this biological filter, and this biological filter actually has 4 sample ports. So the water comes in from the top and floats out at the bottom, and you have these 4 layers kind of where you have this biological system eating, consuming the organics. And when you look at the samples taken from these different ports, you see after ozonation, so this is the feed into the biological filter, after the first layer, you see still quite some upward shift and some absorption in the organics, but after the second filtration step, we're basically done with the consuming of the organics. So the third and the fourth layer are basically not used at this point, and the outlet quality is not changing anymore. And in the end, what they learned from this is how to better operate their filters. They were not flushing the filters that frequently anymore because they've seen that it takes much longer to actually fill them, and so on. And now, after we were done with the survey of the plant, we installed just 2 analyzers, but they are sitting online and monitoring over time, and you see a time span of a few months down there. In orange, the inlet water quality, the UV 254 in this case, and in green, the outlet quality of the plant. And the difference between the 2 lines is basically everything that the plant takes out in terms of organics. And you see high fluctuations at the inlet, very low fluctuations at the outlet. But if you look closely, you can see 2 things. The first one that is not that nice, there is a possible drift. It was not clear if this is coming from the natural background of the water source, or if this has something to do with the measurement itself. But the more interesting part is actually this part here. There was one event at the very beginning where the UV 254, the inlet, went up, and it also went up in the outlet. And luckily, they also were using our alarm system, and this is exactly what the alarm system showed. It immediately picked up this unexpected rise at the outlet and flagged this as an alarm for the operators that could immediately react on this. And with that, I want to go a little bit deeper into this predictive control I was mentioning at the very beginning, to show you how much saving you can actually get from using a system like that. We monitor the raw water quality of, in this case, a lake, could be a river, whatever. We feed this information, DUC, nitrate, color, and maybe a chlorine demand parameter to the dosing system. So when the water reaches the treatment plant, the system already knows what to expect. And the system calculates the amount of polymer that it needs to dose into this raw water to remove the turbidity, the organics, and so on in this flocculation system. And by just adding the right amount of polymer, not overdosing, but really adding just what's necessary, you get a lot of benefits. First, you reduce the energy used for mixing the polymer with the water. you are reducing the chemical amount that you are dosing, so the coagulant, the flocculant, and overall you're reducing the cost of the mixing, of the dosing. But if you're dosing less chemicals, you also have to dispose less chemicals. So you get another saving on the disposal side, which is of course also important if you want to run your plant in a greener fashion. And by adding exactly the right amount of polymer, you can also really meet the turbidity targets that you need for your processes after the flocculation, so for the filters, for example. And by removing all the organics, you can then reduce the risk of disinfection byproduct formation, so this DBPFP. It's proven that these substances that occur during chlorination have a negative effect on health. They can be cancerogenic and so on. So by getting the organics right, or the polymers right, you get the organics right. By getting the organics right, you need less chlorine. By needing less chlorine, you reduce this trihalomethanes disinfection byproducts. So a lot of advantages that you can get. And if you do this in a feed-forward fashion, you're even faster than if you would do it in the feed-backwards fashion. Because if you're monitoring here and feeding this information backward, you're always too late. But doing it in the feed-forward, you get all these benefits. And with that, I'm done with the drinking water works. And now let's go into the distribution network. We have seen part of this already if you watched our pipescan webinar. But let's start with two examples from the United States, if the slides move. Vicky, can you move, please?
Yes,
okay.
of course.
So drinking water security and all, they move quickly, quicker than expected. No. Okay, let's talk about this. So we have drinking water monitoring systems spread out through New York City, and what you see there is a technical drawing of what is built inside these cabinets that you have seen for a second. There's a spectralizer sitting in the middle with a flow cell that monitors the organics, the turbidity, the spectral alarms, has the event detection system. There's the pH probe, conductivity, and so on. Everything is controlled by one of our terminals, and as soon as the system sees something unusual, so an event is detected, it opens a valve and automatically takes one sample, and the information about the event is of course also sent to the operators that can jump into a car and grab this sample and then look further into what was happening there in the lab. Second example is from the city of Dallas, and what Dallas has, they have one of these very nice fully integrated systems. So they have the online water quality monitoring stations in blue. They have customer complaints that would light up on the map. They see alerts, obviously, like this one down there. But they have also integrated the laboratory data into this platform, and they have, of course, access to the real-time view of each of the stations. If they click on one of these stations, they see a gauge view of all the parameters. And as long as the needle is into the green range, everything is fine. In this case, pH would be too low, for example. And if they further click on one of these parameters, they also can see the view over time, where they see how the pH was behaving over the last couple of days and hours. And now, very quickly about some pipescan applications. The pipescan is our monitoring system that sits right on the pipe, monitoring various parameters like turbidity, UV, 254, color, DOC, but the classics like conductivity, chlorine, directly under mains pipe pressure. And how do we do that? We have a straw that reaches into this pipe, that draws in the sample into the analyzer, the pipe scan. This water is passing through a filter, and then it's circled through the flow cell over each of the sensors by a nano pump. And after it passed each of the sensors, it's re-injected into the pipeline. And with that, we do not have any non-revenue water, because water utilities today are optimizing the network for losses as much as they can. So we didn't want to bring another loss of water by adding more and more online monitoring stations. And this is how we imagine how this will look like in the future. Pipe scans or other monitoring systems spread throughout the network. Remember, European Water Directive says source to tap, so they need to make sure that the water quality is right all the time. And installations would look like this. Different types of power supplies. So in this case, there's a turbine, but there is also the chance to work with solar panels, or you have main power supply available at the pumping station, for example. And we are working on making the pipes can run from batteries, so that the installation gets even easier. And now let's look at some data that we generated with the pipe scan. So we have a European city there, a couple of 3 months of data. You see nice fluctuations in pressure. At night, they drop the pressure because there's less demand. At night, they move it up, they increase the pressure. What you also see is that temperature surely rises over summertime. So we start with like 12 degrees, 15 degrees C, and we end up with around 25 degrees C. Remember, the higher the temperatures, the more likely bacterial regrowth is. And everything would not be that dramatic if chlorination would work all the time. But if you look at this one tiny drop here and zoom in, we see that in this example, there was actually a time period of 3 hours where there was no disinfectant present at that spot, which is of course not ideal. And if we would just sample with grab samples manually twice a year, the probability to catch exactly these 3 hours of disinfection loss, the probability would be just 0.07%. And if it would take one sample every week, we would still be just at 1.8% probability to catch it. And in the end, it's combining or comparing taking photos of your house versus video surveillance if you want to catch someone breaking into your house. Next possible application, if you monitor your network closely, you can test the hydraulic models. So you can inject spikes, for in this case of free chlorine, into your network and watch them travel through your network. You also see that the free chlorine is consumed. So at the treatment water work, they add around 2.2 milligrams per liter, and in the network we find 1.5 milligrams per liter, even a little bit less. And this information can of course then be used to be fed back into a digital twin, for example, to fine-tune the algorithms. Next example, and if it's moving. And this is the last example I want to show you, is from Belgium, where they use pipe scans and monitoring stations throughout the network, monitoring all these listed parameters there. And what they like is that they can follow different raw water sources that were used to produce drinking water throughout the network. And in this case, what you see here is for maintenance works, they filled up a drinking water reservoir with a different raw water source. And you see that this has a massive conductivity change coming with it, and the reservoir is filled, and then they start to consume this water. But what is even more impressive was what happened when they had a major break of one of the pipelines. What happened here in St. Peter de Leuven, the main drinking water pipeline bursted, and they had to change the flows to be able to supply all citizens with water. Usually, most water comes from the main vault from St. Peter de Leuven to Prague, and is going to Bruges, and the same over Ghent towards Bruges. And with this major break of the pipeline, they decided to shut the network here at this orange marking, and you see that a lot of flows changed. So they had to supply the maximum available water from the main vault to Prague. The same is true from Ghent to Bruges. They reversed the flow here where you have the orange arrows to be able to supply each and every citizen with drinking water. And they could monitor all these changes throughout the network. In this case, I'm showing you conductivity. In case of these changes here marked as 1, this is where they use the backup source, a backup reservoir to feed into this into the network. And in this area where that is marked with 2, they saw that water was stagnating in the pipelines. So they got a lot of operational insights on the network that helped them to optimize what was going on. And another thing that they were doing on the concubes, which can be easily done, this is the terminal software that you see there, is they calculated something that's called specific UV absorption, which is the coefficient between UV254 and the dissolved organic carbon. And right on the 21st, they had this pipeline break, and you see that this specific UV absorption value goes all the way to 5. And if you look at what this number actually means, a SUVA value between 2 and 4 means there's a medium risk of disinfection byproducts to form, and if the value goes beyond 4, you have a high risk of this formation. And what was interesting for them is that they could pinpoint customer complaints coming in through email, or chat, or telephone calls to this change in the SUVA value. And people call and said, okay, my water smells differently, my water tastes differently. And they were able to pinpoint this to explain the customer complaints. And with that, I'm done with my presentation. I want to thank you all for listening, and I think now it's time for a few questions only, because it's close to 3. Thank you.
That's true. Thank you very much, Christoph. We have time for a very short Q&A. So we have questions coming in. Let's just start with one. Do you think that the SUVE value works generally for predicting odor issues?
No, I don't think that this will be something that is that easy. For them, it worked quite well, but I think that this is something that the water utilities would evaluate for their specific water sources and their specific networks. So no, unfortunately not.
All right, interesting. A second question, where are the event detection algorithms evaluating the data?
So we are not doing it like everybody else does it today. We think that it is more important to run these algorithms on the hardware that is located directly at the water that is measured, for one simple reason, because then you can be very power efficient, and you can still react very quickly to any change in water quality. So when the sensor sees something, it can immediately start transmitting the data, and it's I think that's the more powerful way of doing it. And we are actually thinking about implementing these algorithms directly on the spectrometers and not just on the terminals.
All right, thank you. And maybe a quick third one, can you directly measure the disinfection by products that form during chlorination, for example?
Yes and no. I know that in literature they use two spectrometers or spectral or grab samples, one before the chlorination happens and one after the chlorination. And if you take spectra before and after, you can subtract those two spectra from one and each other. And then you see a signal forming around 260 to 270 nanometers, which comes from this the binding of the chlorine to organics. So it's not really the disinfection byproducts, these substances like the trihalomethanes, because the concentrations are very, very low. But you can at least see the effect of chlorination to the organic matter using the spectrometers. You don't see, for example, the interaction of chlorine dioxide with organic matter in UV spectrometry, but chlorine and chloramines you can see.
All right, very interesting, thank you. With this, we're already at the end of our webinar. All additional and remaining questions will be, of course, answered in written form and will be made available for you to read on our customer portal. Just a quick reminder, a full recording of this webinar will be made available on our website as well. And the third and last part of our series will take place on December 9. We will keep you updated, of course, and thank you so much for joining us today. We are looking very much forward to seeing you next time. Bye.